All right, model building, model eval, not model building, model eval session 2. Here we have our learning objectives. Again, I will start putting everything under here. Our course syllabus is here, assignments, and then you'll see each section as we go along. So in section 2, we can look at our class agenda here. In our agenda today, we are going to be covering confusion matrices, F1 and F beta, which we've talked about before, but now we're actually going to really understand that. And then we're also going to touch on log loss in part 3. So we've completed our introduction and overview, and today we're working through our foundations of model eval. And then I'm also going to do a intro to our first assignment here. You guys have a week and a half. We only have 2 assignments in this class, each one about a week and a half. So the workload should feel a little better balanced. There might be a little more content because we're covering like a wider breadth of lectures in there. So I have that first one up there posted. So we'll go through that. And again, I have the learning objectives in here if you guys want to know what are the things that I really need to take away from this. It's confusion matrices. I forgot to bold that one. F1 score, F beta score, and log loss.
Hey, Emily, we can't see your screen.
Oh, I'm so sorry. Thank you. That would be confusing. Thank you. All right. So what I'm meant to be sharing was our learning objectives here for session 2, the information you'll need to know, and our class agenda here is what I meant to share. All right. This is a reminder for me to do attendance, so give me one moment while I do that real quick.
We got to put through this class.
Let's see. All right, we got Ted, we got Charity, we got Brenda, we got Anna. Yes. Is it Anna or Anna?
I say Anna.
Anna. Okay. Anna.
Yeah, I guess you're both. I'm not picky.
And you're just one N, right? Okay, I've seen it spelled both ways, and I wasn't sure if that was a me thing or.
No, I technically, my first name is technically 2 names, but that's not
We have James.
Yeah, because I'm like, if anyone ever
We
calls
have
me
Matt.
That's
And we have Missy. And John. And other John. Okay. Got it. Awesome. We have everybody. Okay. Assignment 1. Let's look at that.
I'm with my last one. It's more so
All right, so in assignment 1, the first thing I want to call out is the submission. Make it easier on me. I'm learning as we go. Oh, this is actually supposed to say not log loss, but this was before I totally decided the name. Binary classification metric. Sorry, ignore that log loss piece there. Probably have the other one in the. That's the downside with putting them in the Google Drive. When I make changes, it doesn't update. But when you submit your assignment, I'm going to have everybody do it through the same medium. The only way I could think of is just Slack. So just drop it in a Slack message when you submit your assignment. So don't email me. I'm making that change. Just making them all. It's a little easier for me to find because my email, it's a little crazy sometimes. And I don't always know what email to be looking for. So just drop it to me in Slack. That'll be our course submission platform. and put your name here. So first, last name would be helpful to me. Some people have the same first name. We have 2 Johns, for example. So if you put your first name, last name, and then leave everything else the same, that will help me. Okay, so submission stuff, that'll help me be able to separate when I'm looking across everybody's whose is whose, so you guys don't all have the same download name in my when I download it from you. So, okay. The objective for this one is going to cover binary classification metrics. That's what we're starting with in this course, is for binary classification problems predicting 0, 1. What are the metrics? So we're going to have 2 parts here, and one is some theories and theoretical questions. Some, I guess, conceptual questions is maybe a better way to phrase that. And the other part is 2 practical exercises. So the first part, just answer these 4 questions. You can just put the answers here in the markdown, and that's worth 20 points, so 5 points per question. And then we have 2 practical exercises. One is around log loss or logarithmic loss. And in this one, you're just going to, I believe you're just implementing it. Let me just make sure. Yeah, here we are. Here's your tasks. Calculate the loss for each instance of the data set, so each row, and then calculate the total loss, compute the overall log loss of the model. And then interpret what that means and just, talk about it. Just talk about what it means for the log loss to have that value. So here's your data set. I went ahead and put it into Python code for you so you can just access the data through this pandas data frame here. Okay, and then answer these 2 questions. So this is definitely part of that, maybe 2.5 points per question or something to that effect, and like 20 points for the programming stuff. I should have put actual points on here, but this is, can you interpret the log loss above? So I guess that's the same as the question, but how would it change if you change the predicted probability for instance 0 for this first instance here from a probability of 0.9 to 0.6, and talk about that. And what's a situation outside of this where you might select log loss over precision, recall, or accuracy? Not in the context of this problem specifically. We only have 5 records here. I don't know if you can draw any significant conclusions from that, but like in general, just showing your understanding of log loss. And then most of the assignment is in the application scenario, where I'm giving you a situation and I'm asking you to understand the situation from the stakeholder's perspective and try to select a metric. So I talk about a scenario here, fraud detection system, and here's the problem and a little bit of information about it. And here's what the stakeholders want. Here's what's important to them. So here's what you have to do. And what I'm asking you to do here is to develop some code to make a machine learning model on this data set. But most importantly, it's not important what model you select. I will not be grading on the type of model you select. What I'm grading on is you have to have a running model, and we learned that in the last class how to do that. So pull on all your knowledge from that class. So expecting you know how to do that and can use some code for that, but select which metric makes sense for this type of problem. So read this and then think about, should I do accuracy, precision, recall, F-score? And then here's some additional, so you're going to, take this data, You're going to take this data, pre-process it, split it into your training set and your test set. You have to split into training and test set, or you don't have anything to evaluate on. And then implement model of your choice, then use the appropriate evaluation metric for this task and discuss the rationale behind it, and then kind of just talk about what your findings were. So here's the data set here, just made a fake data set. It doesn't really mean anything, but here is the target that you're trying to predict. So was it fraud or not? So again, I gave you the data frame for this. So here is the data frame, and then all of your code will exist down here. Probably don't know what log loss is or any of that because we haven't talked about that. We'll talk about that today. But outside of that, any questions for assignment 1? You have a week and a half. You have 2 weekends.
Does your office hours start this weekend?
Yep, office hours on Sunday. Feel free to show up Sunday. I'll post a Zoom link. I have a Zoom account through school, so I will post a link to like my room on Zoom at 9 a.m. on, I believe that's the time I said. Did I say 9?
Yeah.
9 a.m.
So if we go to Slack, then you have a link.
I'll have a link in Slack. Yes, probably to a Zoom channel or StreamYard. It doesn't matter, but it won't be recorded. I'll put it that way. I won't record office hours because we'll probably talk about homework. I'll probably just do a StreamYard link, but not record it. I'll post to something. It doesn't matter. And then just join if you guys want to ask questions. We can talk about homework or whatever you want, really. All right, so we'll leave that space. Take this homework, look at it. If you have questions, let me know on Sunday or on Slack. Awesome. So again, that's under, if you go to student folder, which should be all that you see. You shouldn't be able to see things beyond that, but you should be able to see student folder and you should see assignments and you should be able to see this here. All right, that was that one. Let's go back to our class agenda. All right, let's get started. We're going to do confusion matrices, then we're going to take a break. Then we're going to do F1 and F beta, quite a bit of content in there. Then we'll do our second break, and then we'll finish out with log loss. And that shouldn't take quite as long because I don't have a breakout session for that section since it's on your homework. Let's kick her off. 1 second, get this all set up so I can see my mouse and look at this screen. There, okay. Wait, you guys aren't always looking at the side of my face. Which is how it normally ends up. All right, so we're going to talk about confusion matrices, or a matrice if you're talking about multiple of them, or a confusion matrix if you're just talking about one. It's like, goose and geese. And then F1 score, F beta score, and log loss. So confusion matrix, it's a table, usually formatted as a table, and it's used to describe the performance of a classification model on a test set which the true values are known. So when you run your confusion matrix, what you're doing is you're saying, here were the results of what I predicted, and these were the actual results. So you can't create a confusion matrix if you don't have ground truth values, if you don't have a way of saying, I predicted 1, but in the real world, it was actually 0. So for unsupervised learning, for example, we can't build a confusion matrix for that. It wouldn't make sense for that. And the intent behind a confusion matrix is it allows us to visualize the performance of an algorithm. Today, we're going to talk about it in the context of binary classification because we haven't touched on multi-class classification evaluation yet. But when we get to multi-class classification, we'll probably come back and talk more about confusion matrices because you guys have already done that with you've already had a look at that with the t-shirt, the clothing prediction problem, but we'll come back and understand exactly how that works. So reminder from last week, we talked about true positives, false negatives, true negatives. We talked about these as outcomes of the model. Sorry, I decided to go to this one first and then flip back. So remember, we talked about a true positive when the model correctly predicts the positive class, true negative, it correctly predicts the negative class, and then the two errors. Because these two are positive, these are the two errors when the model is wrong. It's either a false positive. I didn't touch on this, but you might hear this because I didn't want to throw too much at you at once, but you might hear this called a type 1 error. So if you ever hear someone say, what were your type 1 errors? I try to stay away from that because I think that doesn't really precisely well describe what you're trying to ask. So I tend to say false positive or false negative, just describing what those are, but sometimes people call them type 1 errors or type 2 errors. So false positive, type 2 errors, those are the situation in which the model predicted a positive class, but it's actually negative, and then the false negative, the model incorrectly predicts the negative class when the class is actually positive. So taking all of those that we learned, we can put those together and create something called a confusion matrix, which represents the counts of outcomes of each of those classes. So there's two dimensions, kind of an X and a Y axis to our confusion matrix. And along the X-axis on this dimension is the true class. And on the Y-axis in this dimension is what did we predict? So if we predicted it was positive and it was actually positive, our ground truth was positive, our Y labels were actually positive, then it's a true positive. So that's just how you interpret this. These are all the things we learned last week, but this is just how you put them together in a visual. So if we predicted positive, but it was negative, false positive. If we predicted negative, but it was positive, false negative. If we predicted negative, and it was negative, true negative. And then there would be counts here, like how many in your entire data set. 1 here, maybe 7 here, 12 here, 13 here. And then if you add up all of these together, these numbers together, that should equal your entire data set, which you're evaluating. All of your instances will be one of these representations. Again, this slide I won't touch on because it's saying everything we just talked about, but it's takeaway for you if you want to come back and refer to it. It just says which cell holds which of those values. So when you are creating a confusion matrix, we'll have all of our values here. You can actually extend that out both to the right and to the bottom. So if we look across this dimension of actual positive, we can take the true positive rate divided by true positive plus false negative. So sometimes you will see confusion matrices that have like more information captured in them. They'll have kind of these rates here, but then they'll also have the sensitivity here. And they'll have the specificity here. See, along this dimension, we have the false positives and the true negatives. So you can put the specificity metric there, which is in relation to these dimensions here. Now, if we go take a slice this way, we can look at the false negatives and the true negatives. That's something we didn't talk about because it's not super commonly used, but if you're making this visualization, it might make sense to put it in there. And that's the negative predictive value. See, it's using the true negatives and the false negatives. And then we can look at the precision. So the precision's looking at just this dimension here, the true positives and the false positives. So you can take each slice of this together, and that's how we get those metrics. And then accuracy is looking at the whole picture, right? It's looking at all 4 of these dimensions. It has all 4 of them on the bottom here. So how many were correct out of all 4 of these? So accuracy is in this diagonal corner because it takes into account all of this information.
When would you see a negative predictive value formula that you would use in that? Like just, at a job, but when would you use
When
that?
would you say it again, a negative
The-
predicted
yeah.
value?
Yeah, well, like when would you need to use that?
Oh, this one, the negative predictive value. Well, if I was making this chart, I might put it on there because it'd be a little weird to have like all these boxes filled in and then just have nothing here. My
Yeah.
stakeholder might say, why didn't you put anything in negative predicted value? But this is just measuring how many predictions did you predict as negative that were actually negative out of all of the negative predictions that you predicted.
Right. So I was asking, what's an example that you would need to use that, like in a daily job task, or like maybe, what would be a reason for someone to use that, I guess?
A reason for wanting to know which of your negative predictions, your zero predictions were wrong, might be if you want to know who's slipping through the cracks. So you're trying to predict cyber attacks, let's say, and you want to know who did I predict as not a cyber attacker, but actually was a cyber attacker? Who's potentially slipping through the cracks of my machine and hiding among like the masses of my predictions? It's usually when there's a higher penalty of having an incorrect zero prediction, which I would actually then maybe recommend you to look at like sensitivity or some other metrics. So that's why it's not necessarily
The go-to.
the
Okay.
go-to one. Because if there's something wrong there, then there's probably something wrong like broader. Yeah. It's not as focused on, but good for you guys to know, be aware of.
Is there ever a time where you were trying to predict a bad event and so everything else is good?
Give me, like, what's an example? What do you mean? A bad event and then everything else? Like the majority was,
So, in the bike industry, meter test failure. So you have all these meters you're testing, and you want to take a look at how many are good. The tests will tell you if they're bad. They won't tell you how many are good.
so that in that case, you're trying to predict, are you trying to predict, will the meter fail, or are you trying to predict, is the meter good?
Yeah.
Which of those two?
Well, the obvious tests we do predict which ones will fail. That's what our standard is. We can test the meters, and if a certain number fail, then the lot fails, that type of thing. But how many of them are good, and how many, because then what if the lot's good, then we don't have to test for another 5 years.
Oh, okay.
So there's a benefit to them being good, but if they're bad, then we gotta start looking more seriously about maybe doing a replacement on that lot.
And you want to know in advance, before you test them, how likely it is that they will be bad, or how likely it is they
Because
will
at
be
the beginning
good?
of the year, we're putting together budgets for 2025 starting next month.
That
so
makes
we
sense.
Have to try to figure out, okay, how much money do I need for these replacements? And we gotta look at that whole base, how many are staying good versus how many are going bad.
That makes sense. Yep. So in that case, if you predicted how many would fail, and you had some that you didn't predict would fail, you predicted zero, you predicted they would be good, and they actually did fail, that can have big consequences.
Yeah.
So that would be measured in your negative predictive value.
Did you predict based on the model of the meter? I don't know anything about meters, but like a specific model, or like, in 2000, this came out, but
That's exactly what we do.
Is it? Oh.
When we're doing these tests on these lots, we're taking a certain lot and it was all one type of meter, and then testing a certain number of those to make it statistically relevant for a test sample, and then seeing how many of those are having issues. And then increasing that test if there's a certain level of issues.
Do you tend to use the same, like, so for example, if you just did it last year for some of the meters that went to fail, do you use that same data onto your sample of like what meters?
This year we might be testing a different lots, area altogether.
Okay.
And if that sample was good last year, then it's good for 5 years.
Nice.
So in 5 years, we'll have to retest some of that same lot.
Okay, gotcha.
using machine learning models to predict equipment failure is a very common use case. They use it a lot in in plants and also in trains. I know they'll put them on trains, and that has led to huge cost savings. They can predict when a part is going to wear out before it wears out and causes more damage.
We use those on our power plants
Awesome.
to determine there are sims tests and stuff like that.
Yes.
Circuits that go around taking sensors, and they can start predicting ahead of time if something's going bad or whatever.
Absolutely.
So,
Oh, how cool. We need to talk more about these. It's nice to hear the actual use cases that these get implemented. So if you want to this is just showing, I wouldn't necessarily recommend this. I personally think it's information overload and not so easy to consume. But if you really want to go crazy, you can just keep pushing out these dimensions on a confusion matrix and getting more and more varying views of how your model's performing across different dimensions. So just so you know, there's a lot more other manipulations that you can do, all extensions of this confusion matrix. I won't make you do this, but I just wanted to share with you so that you're aware in case you see a confusion matrix that has some dimensions that you didn't recognize or has more information to it, or if you like this or find this useful, this is definitely a way that you can view this. Yeah, I think it's a little information overload. Personally, I wouldn't know where to focus, but that's just me. What's really useful about a confusion matrix, which we'll do today in our first breakout exercise, is that you can actually use those exact numbers, just those 4 boxes communicated in a confusion matrix, to calculate all of these scores, all of these metrics. So a confusion matrix is a very beautiful thing because it's an incredibly concise way to represent a ton of information. I don't have to know every single prediction that your model made and every single ground truth outcome like I might with some other metrics like log loss, for example. Instead, if you show me a confusion matrix, in my head, I can probably calculate accuracy or I can ballpark it. But if you have a computer or a calculator in front of you, you can calculate accuracy, precision, recall, specificity, which we didn't talk about, by the way. It's just another dimension. Again, it's the true negatives plus false positives. So it's just one of those other dimensions. But F1 score, which we'll talk about more in depth later today. This is relevant. So I was giving a presentation once to a boss of mine, a VP of data science. It was just me and him. It was a one-on-one, and I was showing him my model performance. And I said, hey, here's our model that is predicting how easy a claim is to manage. And if it's a really easy claim, then we're going to send it to some newly trained examiners so they don't get all of our complex claims and aren't overwhelmed, and they can just work on the easy ones while we onboard them, and they can kind of learn the rules of the organization. And he said, you're showing me this confusion matrix, but you're saying your accuracy is this, and that doesn't make sense. And I was confused. He said, hey, you say your accuracy is this, but this is what your confusion matrix says, and when I do the math, they don't add up. And I was like, oh, you're right. I went and looked back at my code, and my confusion matrix was calculated off my training set, and my accuracy was properly off of my test set. And so before I presented this to stakeholders, I was able to, run my confusion matrix off my test set so it matched the same accuracy. So that's just showing you that you can calculate these just straight from these 4 numbers, which is really useful. You can call someone out too if you think it might be wrong. So the breakout here is we're going to calculate our metrics from our confusion matrix. So go download this breakout notebook that says confusion matrix. short lecture there because you guys are already kind of familiar with that, but this should be fun. So in here, we have a function called calculate metrics, and it takes in a confusion matrix, where a confusion matrix is just a list of lists, and the first value in the first list is going to be the upper left corner here. So the predicted negative and actual negative. And then it moves through here, predicted positive, actually positive, predicted negative, actually negative, predicted positive, actually positive. Okay, so then I go and I assign these to these values. So we have true negative equals confusion matrix at 0, 0. What that means is 0, 0 is right here. It's the first position in the first list, this 9,000. And that's predicted negative, actually negative, which is true negative. So I just go through and grab each of these confusion matrix at 0, 1. That is the second position in the first list. And those are the false positives. False negatives is in the second list, the first position. And then the true positives is in the second list, the second position. What you're going to do is using true negatives, false positives, false negatives, and true positives. These are things we talked about last time. Calculate accuracy, precision, recall, and just for fun, I added the new metric in there. You can go ahead and add specificity in there. Again, I have that on this slide. This is specificity. True negative over true negative plus false positives. So calculate those, and then run this, and it should print out your accuracy, your precision, recall, and specificity. It's going to call calculate metrics. It's going to pass this confusion matrix, which we defined up here. And for all 4 parameters, it returns them in this tuple of 4 values, which we are returning right here. All right, let's spend, what did I say on that? I think it's not very much time. Yeah, let's spend 15 minutes on that. We'll come back at 7. All right, checking back in 5 minutes early here. Were you guys able to calculate accuracy, precision, recall, specificity? Awesome. Anybody want to drop in the StreamYard chat your, oh, and we do have a chat thing here, sorry. Oh, I think that was from earlier, perfect. Anybody want to drop in your calculation for accuracy in the StreamYard chat?
I apologize, Emily. I got pulled away for a few minutes, so I'm running a bit behind.
Oh, no, you're good. Take your time.
Thanks.
If you guys, I did stop us 5 minutes early. Do you guys need another 5 minutes? Anybody want to share accuracy?
I put it on the chat, but I think that.
Oh, did you?
Yeah, I just put a screenshot.
Which chat? Okay, perfect. Yep. I never know which chat to look at. Sorry. I jump back and forth. Yep. There we are. True positives, true negatives over true positives, true negatives, false positives, false negatives. So let's type that in here. That's exactly it. So accuracy is going to be how many did we get correct? P, the ones that start with P, the true ones, over everything. All right, does anybody want to share what they did for precision? Excellent, thank you, Matt. Got Matt's answer here. We have precision, which is our true positives over our true positives plus our false positives. How many did we predict as positive that were actually positive out of true positives and false positives? Yes, out of all the ones that we predicted to be positive. So which ones did we predict as positive that we were wrong about? And the ones we were predicting as positive that we were correct about, out of all of those, how many did we predict we were positive or were correct about? Does anybody want to share a recall? Excellent. Thank you, John. We've got recall as true positive over true positive plus false negative. How many did we predict as positive that were actually positive out of all of the positive ones that exist in our data set? So our false negatives are ones that we predicted as negative, but were actually positive. So which of those did we miss, essentially? And the last one, specificity. Anybody want to share that? Perfect. Thank you, Missy. All right, true negative over true negative plus false positives. All right, we're going to run this. And there we are. We have our accuracy, our precision, recall, and specificity for this data set. All right, moving on. I'm going to go another 5 minutes, and then we will take a break. So we're gonna jump into this a little bit here. So F1 score. Let me rearrange my slides so I'm looking at this screen again. Oh. All right, there we are. The F1 score is, sorry. There we are. F1 score is a very common metric used in binary classification. And now we're going to start to put together all of our knowledge. So the confusion matrices were a good review from last week, last Monday, this past Monday, because now we're going to look at a score that provides a balanced measure by taking into account both precision and recall. So there, as we talked about, accuracy isn't always a good metric to use. It has some limitations in that if you're really, really correct on the majority class for class imbalance problems, your performance can be very high, but that doesn't actually mean that you're doing what you want it to do. So our example with fraud, we have 99% non-fraudulent people, 1% fraudsters, and we predict 0 on everything. We predict everybody is a non-fraudulent individual. We get 99% performance. Looks really good. We're not actually doing what we want to do. We're not actually predicting a single person is fraud. So F1 score is a way to measure the balance between the precision and the recall, which would be a better metric for that situation. Just as a reminder, precision recall, quick review from last week. Precision is the proportion of true positives of the predictions among all instances predicted as positive. It's how accurate were our positive predictions. On the other hand, recall measures the model's ability to capture all of the positive instances that exist. Okay, taking those two things, putting them together, here's the calculation for our F1 score. And you'll hear it referred to as this very fun term, which is called the harmonic mean. So now you're going to use that in real life, which is cool. So F1 score is the harmonic mean of precision and recall. And this is the formula. One is usually subscripted, F1. Score is 2 times precision times recall all over precision plus recall. So that's the formula. Why would you use this? The harmonic mean gives more weight to lower values, ensuring that the F1 score remains high only if precision and recall are both high. Therefore, it's more effective at assessing the overall performance of a model in terms of both false positives and false negatives. I should have bolded that part. So it's better assessing the performance of the model in terms of both false positives and false negatives. How might you interpret, you get an F1 score and it's 0.8 or it's 0.3. What does that actually mean? First of all, I should emphasize that the way that this was constructed very cleverly, the score will always range between 0 and 1. Just like your accuracy ranges between 0 and 1, we often convert it to a percentage, so you'll see it as like 85%, but really, it's 0.85. It's a value between 0 and 1. You will see that with most of our metrics. It's an easy way of kind of interpreting those values, so we don't have massively differing ranges that kind of stretch our cognitive ability to interpret those. So this is a scale from 0 to 1. An F score of 1, if your F score is 1, that's perfect precision and recall. You have a 100%, I don't want to say accurate model. You have a 100% performant model is a score of 1. While a score of 0 indicates very poor performance. So 0.8 would be a good performing model, a really good performing model. A 0.3 would be quite a poor model. Okay.
Is it assumed that 0.5 and above is within a good?
That's a really good question. You might want to look at, for your problem set, what does a coin toss mean?
Okay. Which
May not always be 0.5. So I would caution against thinking like an F1 score of 0.6 is bad, for example. You're like, oh, we're barely doing better than random. That may not actually be the case. If we, run a random model to make a random prediction and they get the precision recall of that, it might actually be a lot lower. Kind of depends on the representation of your data set.
But the goal is to be as close to a 1.
As close to a 1 as possible, yes. But it's hard to balance that precision and recall. It's not quite as easy as it is in accuracy. In accuracy, you get a lot of forgiveness from that majority class. You made me think of an assignment or an exercise to do next time, which is creating a random prediction and estimating the baseline. So thank you. That'd be fun. More homework. Not this class. I already have that done for this, but next time I do this. Yeah.
Precision
Oh.
and recall are both factored around TP. Or the percentage of that versus false positives or false negatives. Really what you're measuring is the correlation between false positives and false negatives of the F1 score. Is that correct?
Let me think about that. Correlation. False positives, false negatives. If false positives go up, we falsely predicted it was positive. Do false negatives also go up, or do they go down at the same time? Not necessarily.
Okay.
So if we predicted the fraud example, if we predicted everything was 0, we have a high rate of false negatives, but we have no false positives. So they're not going up at the same time. But your question might be, do you get more, maybe this is your question, do you get more false negatives? You have more false negatives, so does that inherently mean you would have more false positives? I don't think so. I don't think they're necessarily correlated. I could be wrong. I'm open to be proven wrong on that. But I think I could construct a model that just gets everything wrong.
So, but you do have, like in our example below, with the values that we have, that are 94%.
One. Oh, the one we just did? Sorry.
Yeah, the 90% precision and 95% recall. Multiply those together. Since they're both high, it's going to go towards 1. Towards 2, I should say.
We're going to multiply them and divide by their sum.
Multiply them together. Then you're going to divide it by the sum of
Yep.
that, which for just 2 values that are both fractions can be a maximum of 2.
And because of that, because it can be a maximum of 2, and because you're multiplying them together, which can be a maximum of 1, we have to multiply by 2 on the outside. In the situation that they were both 1, then that would sum to 1. So 1 times 1 is 1, over 1 plus 1 is 2. 2 times 1/2 would be 1.
Yeah. Highest you can get in the fraction piece is 0.5.
In the fraction piece is 0.5. And then on the outside, we multiply by 2. Correct.
So it can get to 100%.
So it can get to 100%. That's right.
Okay.
And I'm showing the simplified version of it here. You're probably thinking in your head, why didn't they just construct that so you didn't have to multiply by 2? The answer is it's a more generalized formula. I'm showing the simplified one where we did some math to move things around so it looks pretty and easy. Precision times recall over precision plus recall times 2. But we're gonna We're going to finish F1 here real quick, but then we're going to talk about F beta, which is the generalized form where you can put anything in for the beta value, but getting ahead of myself here. I think you will be curious, John, when we get to that one. Okay, F1 score example. Let's walk through an example with this. So let's consider this binary classification problem where we have the following matrix: 9,000, 100, 50, 950. Might look kind of familiar here. Let's calculate the F1 score for this. So take just a minute and calculate the F1 score. I'll leave it on this slide, but if you guys need the formula, 2 times precision times recall, all over precision plus recall. Well, not all over, doesn't matter. We have to think about that. Over the second half over precision plus recall. I know I said 5 more minutes. We'll take a break. We'll do this one thing, and then I think we're at the end of this. Yep. So then we'll take a break right before F beta. All right, somebody was able to calculate that, drop it in the chat. Chat here. .92. Are we ready for the moment? Here we are. Good job, 0.92. I might round that up to 0.93. So precision, we're calculating as our true positives over true positives plus our false positives. And then we are taking that so plugging this in, true positive 950 plus 100. So that gives us 90, about 90% there. Here's our recall, same thing, but we're doing the false negative here, so that's about 95%. So we can calculate the F1 score by taking 2 times precision times recall over precision plus recall. So 0.90 times 0.95 do all this. So we multiply here, like John said, which will be at most 1. So this is a value between 0 and 1 on the top. It's a value between 0 and 2 on the bottom. So we have 0.85 divided by 1.85. And then we take that times 2. I guess it distributed on the top and the bottom. And then, so our total score is 0.92. So do we see how this is the harmonic mean between precision and recall? 0.927 is probably almost right between 0.904 and 0.95. So it's balancing. It's sort of like the average of these two metrics. Okay, let's take a 10-minute break, and then we're going to talk about the generalized form of this, which is called the F beta score. All right, 5 minutes here. Or 10 minutes, I'm sorry. Come back at 7:21. F beta score. So let's keep going here. F beta, so we should be feeling comfortable with F1, true positives, true negatives, all those outcomes, and also our precision and our recall. Let's start to take it to the next level here. So we built a really strong foundation so that now you can grasp something that and really feel like you understand a concept that is not intuitive to kind of like the general public population, I guess I would say. This is you're very much in the field of statistics and data science here as we talk about our F beta score. So F beta is a score, an evaluation metric that combines precision and recall, and it's a single measure of the model's performance in binary classification tasks. And it's a weighted mean between precision and recall, where beta, the word beta, it's a parameter that controls how much emphasis do we want to place on recall versus emphasis that we want to place on precision. Sorry, I'm going to move my slides here for just a second so I can see the second slide coming up. I never know if I'm going to talk about something that's going to be directly on the next slide. I don't think it is. So when we say an F1 score is a version of the F beta where the beta is the value 1. The beta takes on value 1. F1, where beta equals 1. So that is the harmonic mean between precision and recall. That's where we are weighting precision and recall equally between each other. But maybe there are some situations where we don't want to treat them equally. We want to consider 30% precision and 70% recall. We want to weight them. And that is the F beta formula. It's a formula that generalizes how we might weight precision and recall compared to each other. I would say this is the most fundamental metric in binary classification tasks next to accuracy. I think accuracy is used a lot for a human interpreter. If you say, hey, my model had a F1 score of 0.8, stakeholders don't always know what that means. So you might have to kind of provide some more detail there. But the F beta score is used very widely for the selection of performant models. So mathematically here, this is the F beta score. We have 1 plus your beta, what you select for beta, squared times the precision times the recall, all over the beta squared times precision plus the recall. Okay, I'm going to get the whiteboard out. We're going to put in 1 for beta, and we're going to see how this becomes an F1 score, because it looks different from the other formula. And I'll switch the view here. But keep looking at it, checking that out while I figure this deal out here. Okay, let's switch our view. Oh, I'm on the wrong screen, sorry. Is this me? Nope, wrong one. This one? Okay. Marker. We said switch back to the screen for half a second. We said our F1 score, I'm just going to write this down, is equal to 2 times precision times recall all over precision plus recall. And we said our beta is equal, beta score is equal to 1 plus beta squared times precision times recall all over beta squared times precision plus recall. All right, switching back here. Okay, that's really small on the screen, sorry. But here is our F1 score, here is our F beta. Let's plug in 1. Let's plug in 1 for beta, and let's see how that becomes this score. So our F at 1 is equal to 1 plus beta squared. So 1 plus 1 squared times precision times recall, so that can stay the same, all over beta squared times precision, oh, beta, sorry, I was supposed to put a 1 there, beta squared, so that's a 1 squared, times precision plus recall. Okay? All right, let's simplify that down. So that's equal to 1 plus 1 squared. 1 squared is 1, 1 plus 1 is 2. Precision times recall. All over 1 squared is 1. 1 times precision is also precision plus recall. So here we are. We have 2 times precision plus recall. It is the same, they're the same formula. This is just 1 plugged in for the beta parameter. What's another value we could have? Another common one, that's a terrible marker. All these are not great. You can't see that at all, sorry guys. That looks awful. You get the idea. Maybe you'll see on this one, this blue looks a little better. Let's plug in 2. So let's do an F2 score. That is going to be 1 plus beta squared, 1 plus 2 squared, times precision. I'm just going to abbreviate to P and R because I'm tired of writing those out. Beta squared, so 2 squared, times precision plus recall. So this is going to equal 2 squared. 2 times 2 is 4. 4 plus 1 is 5. Precision and recall. Recall. 2 squared is 4. 4 times precision. 4p plus recall. All right, let's do one more. You guys can't see this one on the screen anyway, so I'll just erase this one. You get the idea though. We're gonna do one more. We're gonna do 0.5. These are the 3 most common values, by the way. So f of 0.5 doesn't mean you can use something else if you want to, but these are just the most common. F of 0.5 is equal to 1 plus 0.5 times 0.5, which is going to be 1.25. Somebody correct me if I'm wrong there. Okay, good. I'm great with fractions. Times precision times recall, and 0.25 precision plus recall. So this one, 4 times precision on the denominator. This one, 0.25 times precision on the denominator. Okay, so different weighting between precision and recall for those values. Okay, I will switch back to the presentation. I have more slides on this. And, okay.
So you want to get more focused to recall, you're doing that by modifying precision.
Yes. When I want to get more, wait, let me think about that. When I want to get more focused on recall, I'm doing it by modifying
That's the only
precision. Yes. Yes. You're always modifying
precision.
that precision weighting. Correct. You only need to modify one of the parameters, and then the other is either amplified by the representation of by the proportional representation in the formula, or by default, the other one has more emphasis. So it is, again, let me try to look at my screen when I talk to you guys. There we are. So beta, when we say what is beta, that's those numbers I was plugging in. Remember, I plugged in 1, I plugged in 0.5, I plugged in 2. That's what the beta is. It's a parameter of the of the performance metric. It's a parameter of the performance metric, not of your model, of the performance metric. It's how you decide you're going to calculate the value. When beta equals 1, the F1 score is calculated. It equally weights precision and recall. When it's greater than 1, the score favors recall over precision. Okay, and it makes it more sensitive to false negatives. I hope that's what I said earlier. When beta is less than 1, when it's 0.5, for example, the score favors precision over recall. Nope, that's the opposite of what I said earlier. Making the metric more sensitive to false positives. If you have a bigger number on the denominator, you know what? We will, this will be a good exercise. When we have our exercise, I have values for precision and recall. I think in our exercise, we actually play with these. So this will be a good opportunity to do that, to really build this foundation. But the text in this slide is correct. So when it's less than 1, it favors precision over recall. Has a higher weight on precision. I'm tempted to keep looking at the screen. So how would we interpret F beta? Again, score 0 to 1. For F1, a score of 1 indicates a perfect precision and recall. I guess a score of 1 for any value of beta indicates a perfect precision and recall. But a score closer to 0 indicates, a score of 0 indicates 0 in either precision or recall. But a score closer to 0 means there's a lower performance across one or both of those dimensions. Here's our example. Let's try it out. Consider an example where you have, where we calculate an F2 score for binary classification problem. Here's our precision and recall. Use the F beta score formula, where beta equals 2, to compute the F2 score. If you have it, just drop it in the Slack chat or StreamYard, whichever one. We'll figure it out. Awesome. John is saying 0.789. Sorry, I have my slides here. I went the wrong way. Oh, I swapped some of my slides here. Sorry. There it is. I was very confused for a moment. Yes, so 0.789 is correct. I might round that up if I was going to say 789 to 79. Or I should have rounded mine 789. Should have all rounded. Anyways, here's the formula. So we have this F beta formula. We substitute 2 in here like we did on the board. And then substitute in our precision and recall here. So our precision, 0.75, and our recall, and then we just math it out. So do all your multiplication and addition, and then we get down to 5 times this number, which is this number here. Excellent. I meant to place this slide next, but I put it in the wrong spot. So in summary, common values for beta include 1, 0.5, 2, corresponding to those. That's the score is usually referred to as F1 or F2 score or F.5 score. Nothing more fancy than that. F1 score is the most commonly used variant. I would say F1 is commonly known in the field. If you end up using an F2 score, you might just have to describe what that is. Not everybody is necessarily familiar with it, though I found it very useful. But choosing that beta really just depends on your use case.
That chosen arbitrarily?
It is not chosen arbitrarily. So I had a situation in which we used the F2 score because our stakeholders, this is again the same, you guys will hear me tell the same stories over and over again. But this is the situation where comments were made on a document and we needed to notify one of 9 different areas: legal, compliance, HR, whether they need to take action on the document or not. And they wanted to be over notified, meaning they wanted a high recall. So they wanted us to recall out of all the documents that they should have taken action on to get as many of those as possible. I want to make sure I'm saying this correctly, so hold on. Yep, okay, good. Just making sure I'm not misspeaking here. I would hate to do that. So we wanted a high recall. We wanted to make sure that of all of the potential actions legal could have out of all the documents that legal should have taken action on, legal was notified of as many of those as possible, even if of the amount of documents that we sent them, of the ones that we predicted that they should take action on, not all of them they actually needed to take action on. So even if there were some false positives in there, more false positives than needed to be, they would prefer to have more false positives, or they preferred to have more false positives than false negatives. Situations where we didn't tell them, we said, oh, you don't need to take action on this, but in reality, they should have been notified about that. That was when we used F2. So that is a situation where you would want to use F2. You want to capture everything that could possibly exist at the risk of inundating your user with too many notifications, because there's a lot of things that maybe aren't relevant to them with that situation. So that was not arbitrary. They didn't actually want equal weighting between precision and recall. They wanted higher recall, and they were willing to sacrifice precision for that. I have not personally had a situation in which I wanted to sacrifice recall in lieu of greater precision, but the situation where you might want to sacrifice recall in lieu of greater precision. it would be a situation where the consequence of telling of saying this instance happened when it actually didn't happen would be really, really bad. So maybe like a tornado alert. I don't know. I'm making something up off the top of my head. That's probably a bad example. You want to be extremely certain. I'm trying to think of something that you want to say with a high degree of certainty. And
DNA
you
test.
say it again?
DNA test.
A DNA test. What are you testing for?
If, I don't know, the child's mine.
Oh, there you go. That's a good point. Yeah, let's do that. That's a great one. That's a good one. We're testing if somebody's child is yours. It's going to be a really bad situation if I tell you that child is yours and the child is in fact not yours. In fact, I might rather, conceivably, say inconclusive or I don't know, as opposed to saying the child is yours when it in fact is not yours. So there might be we might want to be really precise in that situation. When we say something, it has significant weight, concretely in individuals' lives. And so we probably want to have a low F beta score. We want to make sure that the predictions that we do make for that are almost certainly always correct. Always correct predictions. That's what a lower F beta score means. Doesn't mean you're catching everything. Some things are going to get away. There are going to be some situations where we tell somebody it's not their kid, where it in fact is their kid, and that's not good either. However, when we do tell someone it's their kid, you can trust us with certainty that it probably is their kid. So that's a great example.
Okay, I just did the same formula we did for F2, for F5 and F10. And the difference is between the three of them are less than 1%.
For one example,
It was for the 0.7894 was the F2, 0.7979 was F5, and 0.7994 was F10.
for what were your precision and recall?
The same formula we just did. Those 0.75 and 0.80.
0.75 and 0.80. So those are pretty close precision and recall values. Maybe try running it with very extreme precision and recall values. Let's say precision is 0.3 and let's say your recall is 0.9. Let's just be really extreme. And then you're going to get a higher variety of values. But even in those close precision and recalls, 1%. So you said you got 1% difference between these various metrics.
What you're saying in that scenario is either your false positive or your false negative is extremely high.
Yeah. So if there is like in fraud, for example, we're going to have a high proportion of false negatives.
Not unless fraud is low to begin with.
True. But your metric that you use to calculate the false negatives. I have to think about that for a second. How many did we predict as?
Because you're looking at, in order for that to be significant, I'm just trying to think through all the different permutations of the F1 and F beta scores. And in order to come up with something that is statistically meaningful.
No, the false negatives does not, the fraud one is just, precision only cares about the accuracy of positive predictions. So even if your fraud count is very, very low, even if it's 2% of your data set, if you didn't make a single fraud prediction, you have a precision of 0. irrespective of the size of your data set. So if we have a fraud data set, and this is our true, and here's our pred, and we predict 0 for everything. Our let's say there's more in here. Our accuracy is 99%, but our precision is in fact 0. Because precision is the accuracy of positive
Gotcha.
predictions, and since we have no positive predictions,
Gotcha.
there's no precision. And our recall in this situation is also 0 because we didn't capture any positive positions, but imagine a situation where maybe we did make one correct there. But maybe there were like 50 or something actual ones. We would still have a really low precision, and we'd actually have a low recall too. So, okay, maybe that helps. I might have added more confusion with that, sorry.
No, you actually explained it, because now
Okay.
it really matters.
Okay, perfect. So when you predict 0 and it's actually 0, that actually doesn't matter for the model. I'm sorry, that doesn't matter in the calculation of an F beta score. I'll say that very precisely. So these predictions are they're not important to the model. If we want to make these predictions important, we should use accuracy. So that's why it depends on your problem. It's not appropriate for every situation to use an F beta score, but for F beta, if we want to consider these predictions, when we predicted 0 and it's actually 0, accuracy is the metric that captures that.
So if we really wanted to just understand your thing, whatever thing it is you're looking at, you just run all of them. Run accuracy.
Run accuracy then.
F1, run F2, run F.5, and just run all of them. That way you can look at them all, and if something stands out, oh, let's take a look at this. Why is this way?
Honestly, that's exactly how I do it. So what's really cool is in the grid search method, which now I'm thinking I'll plug this in later in the course. When you do grid search CV on sklearn, we've just passed it one metric because we've been working on understanding how this works and putting all this code together. And you can actually pass it multiple metrics, and it can log that for all of your runs. Then when you pop into MLflow, you can see, oh, for each run of my model that I trained, what were my metrics across these dimensions? And for any model that I'm going to train, these are my baseline ones. I run accuracy. I run a F score. Usually, I usually just use F1 unless I have a significant reason to do one of the other ones. And then I run log loss. And just for like a basic run of a model, I look at all those scores. And it helps you really understand exactly like you said. Sometimes I'll get a really high accuracy, and then I'll have a low F score. And I'll say, oh, my model's not actually good. I can tell by the combination of those two metrics, it's just really good at predicting 0. It's really good when my situation isn't occurring, knowing that it's not going to occur. And maybe that's not what I actually want, so then I can tweak things and change things. So that's exactly it. You hit the nail on the head there. I would recommend that. Got to remember where we're at. Oh, yeah, we're doing a breakout. So let's implement F beta. Pop into our class files here. Check out our implement F beta notebook. Go ahead and download that. And then open it up in whatever your working environment is. In this notebook, we have, so I'm just describing the F1 score. You don't need to do anything at the top here. I'm just implementing this for you. So I'm saying 2 times the precision times the recall over the precision times the recall. And that calculates our F1 score. So given 0.8 and 0.7, for example, here is the F1 score. You can play with this. You can change your precision and recall. So we can change our precision and recall to whatever you want in here, and you can end up saying, oh, interesting, 0.9 and 0.3, it generates 0.45, and you can start to understand how that really is sort of like the halfway point between 0.9 and 0.3. So it's kind of interesting. There we are. So what you're going to do is in this example down below, I want you to make this function, this calculate F beta score, return the F generalized F beta formula such that when it takes in beta, it calculates that score. So beta is a parameter, just like we had it as a parameter in, so here's the formula, I'll just go to it. I want you to put this formula into that function. That's what that function should do, is given beta and given precision and given recall, return what the calculation is. So here we have a precision, here's how you'd use it. We have a precision and a recall, and we want to try 0.5, 1, and 2. So this is just a loop that loops over all of them for beta in beta values, and calculate F beta. It's going to pass precision, recall, and then the beta value. So first it'll pass 0.5, and then it'll pass 1, and then it'll pass 2. Then it's going to print them out. So this is at the top here. I put what you should get if it is done correctly, if it's calculated correctly. So go ahead and spend, how much time did I say? I'm at a loss without my, oh, wrong thing. Let's spend 20 minutes on this. I don't want to cut it short. This is the last breakout today, and then we'll wrap up with log loss, and we'll be set. Let's spend 20 minutes on this. Let's make it 25, and we'll go ahead and add the break in there too. So somewhere in here, spend 25 minutes. We'll come back at 8:20. If you need to get up, walk around, stretch your legs, do that before 8:20. I'm throwing an extra 5 minutes in there so we'll just mash these together. Okay. 8:20. John brought up a really good way of just grounding your understanding a little more in these metrics. So sometimes while we're understanding problems, it's fun to play with extreme values. So let's put 9 and 4 here for precision and recall. Now, I don't have anything up here. You should. I ran this earlier with the correct, or with what I had made for the function here, so it's still saved in the memory. So that's why this is running without any code here, if you're curious. But yours should actually have code here, or it will throw an error for you. So if we have a precision of 0.9 and a recall of 0.4, John was noting that the F1 score is going to be right between those, between 0.9 and 0.4, because it's our harmonic mean. It's the balance of those two scores. But if you look at the F.5 score, we have 0.72. It favors precision. It puts less of a penalty on recall, even though we have a really low recall. It's not as low of a score returned from this when our precision is 0.9 for the F.5 score. And that's because the F.5 favors precision. F2 score favors recall. And so you can see that even though we had a really great precision, our F2 score, we get a low score, 0.45, because we're being heavily penalized for our low recall score. Let's swap these and see how these change. Remember, we had 0.72, 0.55, and 0.45. Well, that's interesting. We have 0.72, 0.55, and 0.45. Our F1 score did not change. The F1 score is the harmonic mean between precision and recall. It doesn't matter if precision is better. It doesn't matter if recall is better. If the numbers are exactly the same, it's still that midpoint between them. But now our F.5 score and our F2 score swapped exactly, actually, and such that our F.5 score is now 0.45 because we have a poor performance on precision and we're being penalized for that. Our F2 score is now a higher value at 0.72 because there's not as much emphasis on precision. There's emphasis on recall, which we're actually doing quite good at. So that was good analysis there by John. Wanted to share that with you guys.
Yeah, that's awesome way to explain it. I appreciate that.
John, you got some appreciation for your good thinking there. Give you guys a few more minutes here. That's why I jumped in there. Sorry, 3 minutes over here. I got distracted talking about Hawaii and living off the grid, so we're back here.
That's an interesting topic.
Say that again?
That's an interesting topic for an F1 score or F8.
I got distracted, went in a whole rabbit hole, so I apologize. If I end up working off the, with Starlink, you can work from anywhere. I work from home, by the way, if you guys don't know that, and so sometimes I take advantage of that flexibility and will travel and also work. And just tempted to just move to Hawaii, live off the grid, and use Starlink for internet. Okay. So calculating F beta score. Does anybody have a code sample they'd like to share? Drop it in the chat, either this one on StreamYard or Slack, either one.
I will give you one that's wrong.
Perfect. Let's do it.
All right.
That's an even better opportunity to look at it.
It's in StreamYard.
Perfect. Let's pop this up here. All right, and we're going to run this. And in fact, we do not get, oh, you know what? I'm changed. Does anybody remember what the original values?
You'll still be wrong.
Did I get those right, 8 and 7?
Yeah.
Okay.
You're almost, you said one value wrong,
All right, what is it?
1 plus,
1 plus.
beta,
Oh. I
instead of
think
1 times.
it's because in the very beginning.
Which
Yeah.
one?
Multiply
The very
instead of
beginning.
adding.
This one?
Yeah. Did I do that wrong? Oh,
Yep, here we go. 1 plus. Let's try it. There you are. You were 1 piece away.
Story of my life.
Isn't that the worst, where you have one typing change in your code that's causing an error? No, that's perfect though. So here we go.
Good catch. Thank you.
Yeah, absolutely. Excellent. Great work. Did everybody have kind of a similar answer? Did anybody approach it in a different way? All right. I think it's pretty straightforward for that one. We've got 30 minutes left, so I want to jump to, let me just make sure, I'm pretty sure I always have to check our agenda, make sure I didn't put anything else in here. Great. Yep, that's right. I'm glad I looked at this. I have a few minutes at the end for us to calculate log loss. It's just a pen and paper exercise, but I want to make sure we have time on that. So I'll go pretty fast here through the log loss. And let me just reset up my presentation so my pointer's on here, but I can actually look at you guys. Okay. Log loss, it's typically called, I hear it most often called log loss, but if you want to be very verbose about what you call it, you might call it logarithmic loss. It's derived from the log function or the logarithmic function. And it's an evaluation metric used to assess the performance of a binary classification model. Prior to this point, all we've looked at so far is assessing what is your predicted value, meaning your 1 or your 0, compared to what the real world value is, 1 or 0. This is the first metric we're going to look at that actually assesses the difference between the predicted probabilities generated by the model, not just the labels. So think about that for a second. If we predicted the probability, I'm realizing maybe this is a slightly confusing time to talk about this, but we're just going to push through because we haven't necessarily dove into thresholds, but we touched on it last class. So draw on that knowledge, how we talked about thresholds and how a model outputs a probability. You may interpret that probability as 1 or 0. Remember, we round up. We say if we predicted a probability was 0.5, we round up to 1. Less than 0.5, we round down to 0. However, if you have a predicted probability of 0.6 versus 0.9, those are both going to be 1. We're both predicting 1 in both of those situations. But maybe we want to penalize a model that is less confident about its prediction. A model that predicts 0.6 is less certain that the label is actually 1 than a model that predicts 0.9. If the model predicts 0.9, it's saying, I'm pretty sure this is 1. I've got some high confidence here. There's some evidence to support my hypothesis. If it's saying 0.6 or 0.52 or 0.1, that's almost 0.5. That's almost not able to discern between the labels. We may want to penalize it more heavily for that type of prediction. That's further from 1. That's what log loss does. So mathematically, we can look at the log loss. It's calculated as the negative log of the predicted probability assigned to the true class label. So let's break this down. Here at the beginning, we have 1 over n. And this is just saying 1 over all of the samples in our set. What that's doing is that's taking our average. Basically, we want to calculate something, and then we want to divide by everything we have because we want to take the average of it, the average across all of the numbers. So we're going to, just like in just your regular plain average mean, when you calculate mean, you take what are all the values. Let's take houses, for example. What are all the prices of a house? Take 1 plus 2 plus 3 plus 4. We add them all up. And then we divide by how many houses there were. There were 5. And then we get the average, 2.5. So just like we would do that, in this metric, we're doing the same thing. Remember, we talked about summation functions. We're going to use those here. So we're going to sum this formula starting for all of our records from I to n, where n is the number of records in your data set. And then we're going to divide by n. So everything here, all of this just says take the average. That's what that's saying here. And then there's a negative sign that's going to invert this. But what we're doing for each instance inside of these square brackets is what we're actually running for each instance. So for every single row, you're going to have to calculate this, add it together, and then divide by n. Okay. What are these? We have y at I, which is the actual binary label for the instance. Was it y is the ground truth, and then I represents the instance that you're at. So for the first pass through this, we're going to calculate all of this for row 1, then all of this for row 2, then all of this for row 3. That's what we're adding up. So y at I, is it 1 or 0? So this is either 1 or this is 0. You can think of this as turning on this term or turning off this term, because if y is 0, 0 times log of p at I will also be 0. So this term is only active, is only represented when y is 1. So when we predict 1, then we take 1 times, because 1 times whatever it is always that thing. So then we turn on this term. You think of it that way. So we're going to turn on log of p at I. P is your predicted probability. That's your 0.3, your 0.6, your 0.9. Whatever your p is, you're going to take the log of that. We're not going to go into logs here other than to just use them. You can feel free while you're taking an exam, doing homework, just doing this in your personal life. I recommend this site. Here's the site. Okay, it'll do your math for you. You just say log of 0.5. There you go. You just get your result here. So this is like a fancy calculator. Okay, I would recommend that. You can put the whole formula in here and then just change the metrics. So you can do that if you need to know what a log is. And then in the second half of the formula, so we take the log of that, we say plus to that, we're going to add 1 minus y of I, y at I. So this is either 1 minus 1, which is 0, which then turns this off. So again, this is either turned on or this is turned off. So when y is 1, this one is turned on and this is turned off. This is not calculated. When y is 0, this is turned off, meaning it's not in the calculation, and this is turned on. Okay, I just think that's interesting.
So you're just gonna have 0 plus something or
Yep.
something plus 0 every single time.
Yep, every single time. Where this is actually going to be negative because it's going to be 0, it's going to be, oh, I misspoke. Yep, 1 minus 0, which is 1. Nope, I misspoke. That will not be negative. Yep, you will either have 0 plus something or something plus 0 every single time. And then when this is turned on, so when this is 0, when y at I is 0, then we're going to calculate the log of 1 minus the p of I. Okay, so 1 minus p of I. So if our probability was 0.2, we're going to take 1 minus 0.2, which is going to be 0.8, and that's how we're going to calculate the log loss. Okay? The reason for that, I'm just thinking through this, make sure I'm not going to miscommunicate. 1 second. Yes. It's because it's how far we are from the predicted probability. If we took log of p at I, whether it was without doing this 1 minus when the probability is actually 0, we're actually in both situations calculating the distance from 1. But in this case, we want to do 1 minus p of I because we want to calculate the distance from 0. So just if we want to calculate the distance from 1, it's log at p of I. The distance from 0, it's 1 minus p of I, which is why we either turn this term off or on or off, dependent on whether it's 1 or 0. I hope that makes sense.
So if you had an 80% chance, 0.8, and you predicted 1, and it was 1, then it's going to value that at 0.8.
Correct.
If you had a 20% chance of 0.2, and you predicted false, and it was false, then it's going to still give it a 0.8 log.
That's
That
correct.
is a high value log value because it was a 0.2 instead of a 0.4.
Correct, because in both situations, you were off by 0.2 for the correct prediction.
Right.
Now, if it was, let's go with your 0.8 example again. Let's say it's 0.8 and it's 1, so that's 0.8. But what if it was you predicted 0.8, but it was actually 0? The
Then it's going
true.
to give you a really low log value because you predicted 0. It came up here, y sub I is 0. And your prediction was high for having it, but you still failed.
Exactly, so it's going to
Positive.
penalize much
Well,
higher.
positive.
Yes, and I should have like log values for these things plugged in here so you can start putting that together in your head. But so it's going to penalize much higher because predicting 0.8 when it was actually 0, it's going to penalize the fact that you were really confident about a prediction and you were wrong. That's what log loss does. It penalizes incorrect, highly confident predictions. That's the worst thing you can do in this.
That helps me understand. You do have an example that does do that later on.
Okay, perfect. Oh, here we go. Here's what I was saying. Log loss penalizes more severely for confidently incorrect predictions. This is exactly what we were saying. Sorry, look at this slide. I have a bad habit of that. That's what we were saying. If you predicted 0.8, but it was actually 0, then it's going to have a much stronger penalty there. It's going to be, your metric is going to drop more. Whereas If you predicted 0.5, you said, well, I'm not so confident, and it was actually 0.2, then you're going to have less of a penalty. All right, so log loss, when you have the output of this value, what all of that will sum to, this magical formula is constructed in all ways, such all metrics are in machine learning. I won't say all, most metrics are in machine learning, which is it sums between 0 and 1. So again, we're going to get a thresholded value between 0 and 1. And with a log loss of 0 representing perfect prediction. So you're going to have to flip your model here in your head. Before, remember we were talking about accuracy. You wanted a high accuracy. You wanted 0.8. You wanted 0.9. You wanted these to be good. This is a loss metric, which means that we want to minimize it. We don't want to maximize it. Okay, we want to minimize log loss, not maximize it. So 0 means you did really good. That means there's almost no loss, no difference between what you predicted. Well, if it's 0, it means there is no loss. There is no difference between what you predicted and what the actual labels were. If you have a 1, you have a really bad log loss, okay? It's different, opposite of accuracy. So in summary, a log loss is, time check here. Okay, we're good. Log loss is commonly used as an evaluation metric for binary classification problems. And again, the difference here with this is the first metric we're talking about where it uses the probabilistic output of the model. So what is the probability that the model output this prediction? So if you have, going back to our machine learning class, if we had a model that does not output probability, you cannot use log loss on it. Okay, log loss can only be used with models that output predicted probabilities. There has to be a value for it to use there, saying how confident the prediction was. Okay, let's see. Let's walk through an example. This is going to be not a coding example, but this is just going to be a write it out example, and then we're done for today. So consider this binary classification problem. We're predicting if an image has a cat in it or not. The cat is the positive class. No cat is a negative class. We have 100 images in our data set. Here are the predicted probabilities for 5 different images. So we have the first image. We predicted that it was a cat with a 0.9 probability. In reality, it was a cat. For the second image, our probability was 0.3, and it was not a cat. For the third image, our predicted probability was 0.6, and it was a cat. We're very confident about that one. And for 0.4, our predicted probability was 0.8, but in fact, it was not a cat. So that was not a good situation for us. Image 5, our predicted probability was 0.1, and in fact, it actually was a cat. Again, not a great situation for us. So for each of these images, calculate the log loss for each one, sum those together, and then divide by 5. This will take a minute. You may have to open, I'll leave it on this slide, but you may have to open the slide deck so you can jump back to the formula. I'll show it here real quick. Sorry. So here's the formula again. -1/n, summing log p of I times y plus 1 minus y times log 1 minus p of I. Pi, sorry. Okay, jump. You may have to open the slides. Or you can just look on the internet, formula for log loss. I'm sure it'll come up. Spend let's spend 7 minutes on this, and then we'll come back and we'll discuss. I may have misspoke here. We're double checking. I think the way I wrote this in the slides, I assumed log base 10, and it may be natural log. So give us just one moment. It's safe to assume that most of the time, for anything that we do, it's the natural log. Log base 10 is not often used in these metrics.
But the formulas on the internet do show your formula with log.
With log, but does it have a little 10 under it or no? So it's going to say log, but it's almost always going to be natural log. I think is the answer. Let me keep looking. I think you're going to have to assume it's actually natural log.
Okay.
That's such a great question though, because when I pulled up Wolfram, I used log there too, and that will get you the wrong answer. Oh, okay. Basically, the natural log is really easy when we're taking derivatives of things, which we will not do in this class, but it is extremely important for backpropagation and neural networks, many minimization algorithms. That's what I'm reading so far. We're lazy, basically. We will make life easier. I don't want to carry a bunch of terms with us. Such a great question, though. This is why we calculate these things by hand, though, by the way. So we know this stuff. Otherwise, you'll just go through life like me, thinking it was regular log base 10. Let's see, predicted probability K. It is the natural log. Can confirm. I'll share my article I found here. It's just this one. I looked at some other stuff too, but this one uses has the formula spelled out with the natural log. But you're probably still going to see just log when you look things up. So just keep that in mind. I think everything we do, if I ever put log on the slides again for any other formula, which I think I will later when we do multi-class classification, assume natural log there as well. All right, so when you guys are going into, if you guys don't remember from class, oh, I already have it open. If you don't remember from, when do people do logs? Is that trigonometry? If you don't remember from trigonometry, ln is the natural log. So if you do ln, that should give you the actual number that you want for 0.5. Or in this case, you'll have to run that calculation there for that one. Okay. Oh, look, I used all our time, so we're just going to jump into it. Does anybody want to share what they got for the image one?
0.1053.
0.1053. Excellent. So if we remember our formula here, we're going to take the negative, don't forget your little negative here, of 1. So in this case, our actual label is 1, okay, and our prediction is 0.9. So since I should have put the formula on here, I'm realizing, so sorry, this is confusing, but with all the 1s, looking back at our formula, we're going to put a 1 here and a 1 here. So this is going to be 1 times the log of 0.9 plus 1 minus 1 times the log of 1 minus 0.9. Now, you don't even have to calculate this second half. You don't even have to put in 1 minus log of 0.9. Just scratch that off because 1 minus 1 is 0. So save yourself some time and don't worry about the infinity stuff. So if we take, so just delete all of that. So 1 times the log at 0.9. So here we have negative 1.105. I hope that's what I got here, 0.9. So we're going to go, here we go, negative 0.105. And now we have 0.105. Okay, so now, is anybody able to calculate all of these, add them together, and divide by 5?
No, but I am confused on one small.
Oh yeah, please.
What happened to the 1 over 100?
Oh, sorry.
Which we're only doing it 5 of those. The
Yeah.
entire set was 100, but these
No, you're right.
smaller probabilities were 5 of them. So we're only using 5 of them.
Yeah, that's such a good point, though. There we go. My bad.
So
Okay.
can you go back to the formula and then explain that part if it's.
That's a good. Sorry about that. I see how that could be. Yes, you're both right. We are only predicting it for 5 of them. The data set is 100, but I can see how that would be really confusing. For the N, are you supposed to use 5 or 100? I apologize. So I changed this. We're now only predicting probabilities for 5 images. And so when we go back to the formula, this should be 5, not 100, or you will have a really messed up metric. And you should be summing together 5 different numbers. If we had 100 values that we had calculated the log metric for and we added them all together, we would then divide by 100. But yeah, we only have 5, so excellent point. I'm sure others were confused about that and appreciate it. Okay. Is anybody else able to calculate the? That's okay. We're going to jump to it. So I'm not going to go through this. This is just for you. You can come back and look at this later. This is how all that was calculated. Basically, what you get is we're going to add all these numbers together. So 0.105, 0.522, 0.511, 1.609, 2.303, and then we're going to divide. We're going to add all those up, and we're going to divide by the number that we have, 0.8. I'm wavering in my assumption here that log loss ranges from 0 to 1, so give me just one moment. Log loss is not restricted to the range of 0 and 1. It can take on any positive value. Don't listen to what I said earlier. Because this value here indicates that does not range between 0 and 1.
That was our worst one, though. That's when we said it was 0.1 chance of not being a cat.
Yes.
Of being a cat, but it was a cat.
So this is, we said 0.1, which is terrible situation. We said, I'm really, really sure it's not a cat. It doesn't look at all like a cat. and it in fact was actually a cat, which is not a good situation to be in. And so this is our highest loss. Remember I said we want to minimize loss. We want to get it as low as possible, as close to zero as possible. Loss does approach zero. I was right. I was correct in that. I incorrectly stated that it ranges between 0 and 1. It does not range between 0 and 1, but as John was saying, this is kind of like that higher end of that value you can expect to it. We predicted 0.1, and it was actually 1. So this is a really, really high log loss.
So if we were bad on all of them in here, we would have had somewhere around 12.5 divided by 5. So it's not high. It's not like there was going to be 10 ever.
Yeah,
It still will be probably between 1 and 5.
and
Or
it's
0 and
still
5.
it's still low, and that's why I actually technically got this wrong. I thought it ranged between 0 and 1 because I've actually never personally in my work seen a log loss go above 1. I actually didn't realize it could go above 1. I have never worked with a model that is so confidently wrong consistently, to your point. Not just confidently wrong once or twice, but consistently confidently wrong. And in fact, I would say in practice, you'll probably never run into that, because if your model is consistently confidently wrong, all you need to do to make it correct is take the inverse of whatever it's predicting. So it's probably not actually going to happen unless it was like you truly flipped the predictions somehow. Anyways, that's a tangent we don't need to go on. So here's the overall log loss for this. It's 0.8, which I should give you some metrics for understanding what a good log loss is. That's not a very good log loss, just so you know. We want it to be close to 0. So interpreting maybe a log loss of like 0.2, 0.3, that's going to be in your better, more comfortable log loss range. A log loss of 0.8 is not a good model. So that's not doing well. Oh, that's my last slide. Great. And we're at time. Excellent. If there are questions, come chat with me on Sunday or drop me a question, drop me a message in Slack. You guys have your assignment. You have a week and a half for that. So that is not due next Wednesday. It's due the following Monday. Excellent. Thank you, guys.
Thank you.